afternoon, ladies and gentlemen. My name is Sewan-so and I'm from LGchem. Today I'm going to talk about the unconventional OLED structures with high performances. And next. We'll start from the introduction of conventional OLED devices, and we'll follow the new materials that we are using for as a core injection mechanism. And next we will move to low work function metals as an anode, not as a cathode. And I will move to the inverted OLED structures and some other approaches, and I'll finish the talk with summary. As you might already know, there are many OLED devices, commercialized OLED devices, which will stick to mid-end display applications. And some of the high-end device applications will come out soon, equipped with LTPS polysilicons. But the degree of development in the low-end side is still delayed. For example, for the lighting application of OLED, the device longevity and production cost and efficiency is still far below. Although the device longevity and same situation exists in the high-end side, is more serious in the low-end side. This is the conventional structure of OLEDs. As you might know, the anode is typically high work function ITO, and since most of our applications use bottom emission type, the anode should be the transparent. And the cathode is the bilayer cathode structure using lithium fluoride and aluminum. And typically there are 4 layers from HR to electron transport layers. And in conventional system, this is very similar to what Kodak people published in 1987. The copper PC was the hole injection layer, which will stabilize the interface between ITO and organic layers. And they used the hole transporting layer made of arylamine type and electron emitting layers in previous times like ALQ3, and also they use ALQ3 as an ETL. And the mobility of electron was quite slow compared to the mobility of holes. And nowadays people trying to fix those problems, and they like to delay the hole mobility, also like to increase the electron mobilities. So let me just show one result that with the device made with the new material. We call it LG101. It's a commercialized material. And this is a device structure. We use here ITO as an anode and lithium fluoride aluminum as a cathode. And LG102 is another our commercialized material, which is typical arylamine type hole injection layer. And this is the drying voltage of the conventional device with arylamine type hole injection layer. For 100 milliampere per square centimeter, it requires a little bit about 7 volts. It's kind of typical device performance. But when we substitute this hole injection layer with totally new material called LG101, then you can reduce the drying voltage. For 100 milliampere per square centimeter, it requires about 5.5 volts. So we can get the low drying voltage, but the problem is, as I just mentioned earlier, the hole pumping ability of LG101 is very strong, but the electron pumping ability cannot match the hole mobility of this system. So there are some mismatching of the carrier mobilities. Next. This shows some very interesting injection ability of LG101 for active matrix displays. We made some devices, single layer devices. We use ITO, and we just the arylamine type NPB as a single layer, and we induced just single carriers. Here, the holes. And when we apply the voltage, the hole should be injected into the NPB and should flow the positive current. But we treated this ITO with nitrogen plasma. People nowadays, most of them treat the ITO with oxygen plasma to make the work function high. But instead of that, we use nitrogen plasma. So we lower the work function. So as you can see, as the red line, there was almost no charge injection from nitrogen plasma treated ITO into MPB. But when you use the LG101 just in between the MPB and nitrogen plasma treated ITO, you can see huge injection here. And I will talk about that a little bit later, why it works like that. And this is the device lifetime. With the new HIL, we put like 500 angstrom thickness of HIL. And when you apply 100 milliampere per square centimeter, it's kind of acceleration test. With ALQ3 as an emitting layer, the half-life time lasts about 900 hours. And when you use also argon oxygen plasma, it will give about 200 hours of device lifetime. But it gave the worst result when you use it, when you treat the ITO with oxygen plasma. This is kind of a reverse data that other people obtained. So we checked the surface of the ITO after we treated it in various kinds of plasma cleaning conditions. And we use oxygen plasma and nitrogen plasma. And we use low power and low gas flow, and high power and high gas flow. And when you use low power and low gas flow, it gave very strange result. We can see some contents of nitrogen atom on the surface of the ITO. And also we saw some deficiency of the indium metal atom after we treated with nitrogen plasma. So this is the XPS data. When you check the surface of the ITO with XPS, we found two different species. One is nitrite and the other one is nitride. So what people insist is that when they treat the ITO surface with oxygen plasma, the concentration of the stoichiometry of indium, tin, and oxygen is same at the surface region of the ITO and bulk region of the ITO. So when you apply the voltage, you can minimize the drift of the metals caused by the different stoichiometry. But instead of balancing the bulk and surface stoichiometry, we create the different surface composition. Next. So that surface composition, the nitride, we think can prevent or at least slow down the metal drift from the ITO side into the organic side. That might give such a long device lifetime. So I just showed the effect of nitrogen plasma, which can give the low work function ITO surface rather than high work function. How about the other extreme cases? This is the direction where all the people, not most, all the people want this direction, high work function anode. How about this direction? Does anyone want to go to this direction? Like this man surrounded by red shorts. If you can go to this direction, there are a bunch of metals you can use, including zirconium, indium, aluminum, silver, and other metals. Very inexpensive metals also, and these two are most reflective metals on the Earth. The reflectivity in the visible region is about 95%. How it can be possible? This is the conventional mechanism. When you use the conventional HIL system, the injection mechanism is overcoming the barrier for the hole injection. The holes from ITO injected into HIL, the Homer level of HIL. So when you treat the ITO with oxygen plasma and when you make the work function of ITO high, then the work function moved to this direction. So it will reduce the injection barrier from ITO into the whole injection layer. That's the reason why everybody wants to treat the ITO with action plasma. But this is our injection mechanism. We call it just HIL, although it's not HIL. The hormone level of LGHIL is down there, more than 9 electron volt. And this is about the lumen level. So when you make a contact of this LG101 with conventional HTL, for example, MPB, there is a charge transfer from MPB to LG101 because MPB is a material which can be easily oxidized. Since the hormone level of LG101 and lumen level is located around here, you have spontaneous charge flow with very small injection barriers. So when you just apply a voltage, the electron flows from this interface into the anode side. This is not anode anymore. And the holes are generated at these organic interfaces and move to the emitting layer. So it means that in the previous time, the anode was located here. But if we use this injection mechanism, anode side is not here anymore. The anode side is located at the two-dimensional space between the HIL and HTL. So there, you don't need to worry about the metal, oxide, and organic interfaces anymore. So by using this mechanism, you can lower the driving voltage. And people have thought that there was no more transfer development of this HIL. But it was not true. Still, this interface has not been that good. But if you use this mechanism, you can do totally new things. Next. For example, I mentioned about the lower function metals for anode. If this is the typical structure for the top emitting OLED, you saw this kind of structure from the PDA system from Sony. It was commercialized last October. And for the top emitting OLED, you need reflective anode. No more highly transmitted anode, because the direction of light should go that direction. So how can you make the reflective anode? The ITO is very transmitted. So maybe you have to do multi-layer processing to make it reflective. But if you can use aluminum as an anode instead of ITO, it can be solved very simply. Just deposit aluminum, either by thermal or sputtering condition. Then you can form the aluminum anodes very smoothly on top of any kind of surfaces. Next. This is the data obtained from the aluminum as an anode. We use glass as a substrate, and we deposit just 100 angstrom of aluminum as an anode. And we put LG101 and the conventional device structures with aluminum, lithium fluoride and aluminum as a cathode. So, since we used 100 angstrom thickness of aluminum, it's semi-transparent. So the light comes out through that direction because this is very thin. And as we know, the work function of aluminum is 4.26 electron volts. But as you can see here, for 100 milliampere per square centimeter, you require 6.25 volts. I don't know what kind, if you are working in the OLED area, what kind of driving voltage you can get for 100 milliampere per square centimeters with AX3 as an emitting layer. But we got 6.25 volt at this time. Next. And also we used silver as an anode instead of aluminum. Silver works even better than aluminum. And as you can see here, and there are linear relationship between the current density and luminescence. Although we cannot measure the direct L value, since the anode side was semi-transparent to measure the IVL curves. Next. And this is a device lifetime. And this is a very practical device. It not just only showing the very peculiar anode structures, but it gave very good lifetime. At this time, we got about 300 hours of device life. Our best optimized devices with nitrogen plasma ITO was about 8 to 900 hours, but at the time we got 300 hours, and with silver we got over 500 hours. And we work harder to find the condition how to make this aluminum anode to work better. So this is the device, our more recent device. For 100 milliampere per square centimeter of quorum density, now we are below 6 volt. And at 100 milliampere per square centimeter at quorum density, this is 50%, and now we got 900 hours. So it's very, this device gave a long device lifetime. As I mentioned earlier, we tried to find the best device fabrication condition for the ITO devices, and we found out that it was nitrogen plasma. And at the best condition, it gave 900 hours. But if you just sputter the aluminum on top of the glass, you can get that up, because we didn't do any kind of plasma cleaning on the aluminum side. Just deposit it and just deposit other organic layers. Also, we took out these devices, not these devices. After we deposit aluminum, we took out the aluminum deposited glass outside and exposed it into the oxygen condition and oxidize the surface of the aluminum. And after that, we deposit organic layers, but it behaves like that. So you don't need to worry about the oxidation of aluminum. So it means that you can do processings that you want after you deposit aluminum, and you can etch it out as you want it and deposit the organic layers, and you can get this kind of data. Next. Lifetime drying voltage is very important, but how reliable device can you make? That's more important. Otherwise, the production yield will be very low if you cannot do these kind of things. So what we did is, we made a device with the LG101, the magical HIL, and we deposit 80 angstrom of aluminum as an anode, and 80 angstrom of aluminum as a cathode. So it's semi-transparent for both directions. Okay? And there was no ITO inside. Intel insisted that there are Intel inside, but in our case, no ITO inside. And we use aluminum for both anode and cathode. And we made this large device, a 7 by 8 square centimeter size of OLED device. It's just 1 pixel. And as you know, there is one tiny pinhole, just one tiny pinhole in this whole device. There will be a leakage channel, and most of the current will flow through that leakage channel, and sometimes it will burn down this whole OLED device. Otherwise, it cannot generate light. But before we apply voltage, you can see the name card across this device. This is semi-transparent, since we use just 80 angstrom thickness of anode, aluminum anode and cathode. But when you apply voltage, you can see the light coming out very uniformly through all these 7 by 8 square centimeter OLED devices. Next. And let me move to the next topic about the inverted OLED. I just mentioned about how easily you can make the top emission devices by using aluminum as an anode when you introduce LG101 as a hole injection layer. And this can be a typical top emitting device without this aluminum as an anode. As I told, if you use this one, you can use aluminum as a reflective anode. But how about this? To make the transparent cathode, also you need multi-layer. What kind of metal you can use? You cannot use aluminum anymore, because if we use aluminum as a cathode, although it's very thin, the last amount of surface plasma effect. So you will reduce the transmittance. So people use like cesium, calcium, or magnesium, or their alloys, or some other metals with ITO on top. And at least you require two different cathode layers, one by thermal evaporation, the other one by sputtering. How about this? Still you can make the device with very refractive cathode system here, aluminum. We use aluminum in this case as a cathode, with ITO as an anode. In the previous time, we use aluminum as an anode, but in this case, we use ITO or I0 as an anode. And what's the difference? Difference lies here. Aluminum lithium fluoride system, we also use aluminum lithium fluoride system. Aluminum lithium fluoride system has been known as the best cathode material. And people believe that if you deposit lithium fluoride followed by aluminum, then high energy aluminum dissociates the lithium fluoride and it generates the lower function lithium. And people thought that the lower function lithium just acts as an injection material for the cathode, not aluminum, or as a lithium fluoride itself. But if you make device like this, you deposit aluminum first and deposit lithium fluoride after that, then it means that lithium fluoride do not have a chance to be exposed to the high energy aluminum. Because just after the deposition of lithium fluoride, the next processing is the deposition of low energy organic molecules. Okay? Then this device should not work. And next. But we made the device with aluminum, lithium fluoride bilayer structure. The deposition of aluminum was first, followed by lithium fluoride deposition. And we use our ETL material. Also, this is commercialized ETL material, and EML, and NPV, and LG101, and ITO, IZO. And you can make the light emitting diode. Although you make cathode system at the bottom of the device, and although you deposit this anode by sputtering just directly onto the organic molecule, onto the LG101. What effect you can get here? We use our EMR, which is under development, without doping at 100 milliamperes per square centimeter. As you can see, it gave about 7,000 nit. When we optimize all of the things together, it gave about 7,000 nit. So it means about 7 candela per ampere without doping. But when you make the inverted structure, it gave about 12 candela per ampere without doping. And although we spurted the IZO or ITO on top of the LG101, the device works. The reason is due to the crystallinity of LG101. This is highly crystalline material, and this crystallinity prevents the damage of the organic molecules, especially the whole transporting material and emitting material, from damaging from these spurted targets. Next. And how about the lifetime? We start to measure the device lifetime at 5,500 nit without doping. It requires about 50 milliampere per square centimeter. And as you can see, the drying voltage is a little bit over 4.3 volt. So I don't know how many of you can make this kind of device without doping or with this lithium fluoride, even with the bottom emission time. Maybe one way is maybe you can use the PIN structure, but this is not doped system. And this is the device lifetime. Bottom there is 50%, not here. So it will require thousands of hours to reach 50% of initial brightness. And we never expected this kind of behavior. We also expected that the drying voltage will go up. But as you can see here, drying voltage is stabilized. even after hundreds of operation hours. So this device, by using this device, at least from the green device, you can get the light output enhancement. And still you can maintain the low driving voltage and good lifetime. It means if you can use this device, the cathode is bottom there. And if you use amorphous silicon for the TFTs, since the amorphous silicon is N-type, unlike the polysilicon which is P-type, you can directly connect the cathode, which is at the same plane of the drain side of your TFTs. So the processing will be even easier. Next. So let me give you a couple of more interesting things. This is the just simple device without changing any anode or cathode, but showing the just EML itself. The meaning of this is we drive this device at 200 milliampere per square centimeters, and the size of the device was about 6 square millimeters. If we convert this size to 10 by 10 square centimeters, then it means that we are pumping 120 watts of power into these organic devices. So organic molecule is now holding these powers. And look at this device lifetime data. This is down there is also 50%. This is 500 hours. It lasts extremely long. If you touch this device, your finger will burn because the efficiency of OLED device at this time was not that good. So you are pumping extreme amount of current with the drying voltage, which is about 6 volt. Although this is red, you need only 6 volt for 0.2 ampere per square centimeter current density. So to compete with current technologies, this means the just inorganic LEDs or light bulbs, the devices, something like that, you need low drying voltage. The inorganic LED has low drying voltage. So the one way to increase the efficiency of OLED devices, keep lowering the drying voltage. Another one is high quantum efficiency. People are trying to use the triplet devices. So by using the triplet molecules, you can increase the high quantum efficiency. But also, if you can inject more current into the fixed areas, then you can make a device which can be driven at very high brightness level. Next. And the next thing is about the substrate that we are developing. At this moment, I cannot give us some other more information, but as you can see, we can make the nanometers. This is substrate, and the diameter of these nanometers is about, you can control it. We can control from like 200 nanometers to 400 nanometers. So you can cover the visible wavelengths. By using that, you can maximize the outcoupling. Because as you know, OLED are suffered from the internal refraction. The portion of the light coming out to the viewing direction is only 1/2 n squared, and the n is the refractive index of the medium that you are using. So use only 1/4.5. That's the portion you are using for the OLED devices. But if you just create a chaos at the substrate, then you can increase the light output. So by minimizing the total internal refraction, you can improve the device efficiency further. So these are the methods that you can make the high efficiency OLEDs to compete with current technologies like LCD at the high end product, like light bulb or fluorescent lamp at the low end device levels. And believe it or not, the market size of the lighting itself is about $70 billion at this moment. So that's a huge market, but still the technology for OLED is not there. So these are the methods to make the dream come true. Next. And this is a summary. Introducing a new material and gave a new mechanism of hole injection, and you can use different anodes instead of nickel, gold, and ITO. And it will give you a flexibility of the device structures, and you can make different devices with a high performance. So it will give you more freedom when you make OLED devices. Next. And these are my colleagues. And this picture took more than a year ago, and as you can see, about half of them are female. But the reason is because in the previous night, most of the male researchers are overdrunk, couldn't get up early in the morning. So I'd like to thank to my colleagues who did these kind of beautiful jobs. Thank you very much.